that is confined in the interval 0 to pi. And the distribution is translational invariant in this interval. So there is this nice periodicity, and this will help a bit the analysis. So most of the examples I will discuss will be in the periodically driven in case, even if the other case is not so different. Okay, so the question of the presence of universal features in spectral quantum systems is definitely not new, has been studied very thoroughly, especially in the 70s and 80s. Back then, the focus was mostly on a few particle systems, and a very extensive study led to formulate two very interesting conjectures on the behavior of the spectrum of quantum systems. So one of them is known as the quantum chaos conjecture, and it basically states that the spectral correlations of few particle quantum systems with chaotic classical limits match those of random matrices with the same time reversal symmetry. So this is a very powerful conjecture. It basically says that the spectral statistics, the spectral correlations are extremely universal. They don't depend on any of the microscopic details of the dynamics. They only depend on some macroscopic symmetries of the time evolution operator or of the Hamiltonian. So yeah, this is a big statement. The second conjecture, which is somehow complementary to the first one, is known as the Berry-Tabor conjecture, and it states that the spectra of few particle integrable systems are uncorrelated. So they behave as Poissonian events on the energy line, if you want. Well, note that the eigenvalues of random matrices are strongly correlated. They show strong level repulsion, for example. But later, these questions have been investigated numerically with the advent of more powerful computers. And in this way, we could also study the same kind of questions, but in quantum many-body systems. And interestingly, what we saw is that these conjectures not only hold for few particle systems, but continue to approximately hold also in the many-body case. So we can here I'm listing just a number of numerical studies on the matter. This is just a very small selection, and I'm just giving priority to the first ones. So in the context, so since similar behaviors have been observed in the context of many-body systems, we can update, if you want, the previous conjectures and change them as follows. So we can formulate a new quantum chaos conjecture, which also applies for many-body systems, which is the spectral correlations of generic, and by generic here I mean non-integrable, quantum systems match those of random matrices with the same time reversal symmetry. And covertly, some sort of generalized Berry-Tabor conjecture is that the spectra of integrable systems, or also of quantum many-body integrable systems, are uncorrelated. But so this is a very generic statement. So let me enter a little bit more in detail and describe what is that we concretely expect from a quantum many-body system. Doesn't work. Okay. So to be more concrete, let's consider a certain measure, a certain way of studying quantitative measure of spectral correlation. In particular, let me look at the following quantity, which is called the spectral form factor. So the spectral form factor for times that are strictly larger than 0 can be written as the average over some external parameters, which I will discuss later, of the absolute value squared of the trace of the time evolution operator to power t, which, if expanded in an eigenbasis of the time evolution operator, can be written as follows. So this quantity is very interesting for many reasons. First of all, let me comment on the role of time in this quantity. So time here is actually not a real time. It basically gives us a way to measure, to probe spectral correlations on different energy scales. In particular, large times correspond to small energy differences. So if we look at large times, we are looking at small energy scales. And this then probes, for example, level repulsion, if there is. Instead, if we look at small times, then we're looking at large energy scales. And in this way, we can probe, for example, spectral rigidity, so the macroscopic distribution of the levels, not only the spacing of two neighboring ones. So of course, this quantity is related to the to multi-point functions of the spectral density, and more precisely, this is the Fourier transform of the connected two-point function of the spectral density. So this means that it doesn't characterize all possible spectral correlations. It doesn't characterize, in particular, multi-point spectral correlations. But to do that, one could slightly modify this quantity. Instead of looking at the average of absolute value squared of this trace, we could look at the average of the absolute value to the power 2n. So these things are called higher moments of the spectral form factor, and can be written in terms of Fourier transforms of multi-point spectral correlations. Okay. But let's look at what this quantity would display for a generic system and for a random matrix ensemble. So let's consider first the case of non-integrable systems. So for non-integrable systems, we need to look at the predictions of, again, random unitary matrices. And depending on whether or not there is time reversal symmetry, we need to look at the prediction of the so-called circular unitary ensemble of random matrices, for which the spectral form factor reads like that. It's a very simple exact result. While instead, for systems where there is a time reversal symmetry, one has to look at the prediction of the so-called circular orthogonal ensemble. And for that, the spectral form factor reads like this. Apart from some contributions that are small for large times or system sizes, it's just 2 times the previous one. Probably I didn't mention before, n here is the size of the random matrix. Okay, but so what happens if we look at a real system instead? So we have this prediction of random matrix. That's, for example, consider the first one, doesn't matter. What will happen for a generic system? So for a generic system, what we expect is something like that. So there will be, for short times, which correspond again to very large energy scales, there will be some non-universal behavior. So this behavior here, which is not agreeing with random matrix. Then there will be a certain time, which is typically referred to as tau-less time. So here I'm calling it tau t, after which the system will start following the prediction of random matrix. So I just look at this curve. So I will have a linear ramp, and then I will have a saturation. So the point at which there is a saturation, which corresponds to when time reaches the size of the random matrix, is typically referred as a Heisenberg time. And it's basically the inverse. So it's the size of our Hilbert space. So it's the inverse of the mean level spacing. So instead, in the case of integrable systems, the prediction is again very simple. So if one has uncorrelated energy levels, at least for large enough matrices, one has that the spectral form factor just becomes a constant that is equal to the size of the matrix. This is the prediction of the Poisson distribution, if you like. So once again, then, if we look at a real many-body or real integrable, quantum integrable system, we will see something like that. So there will be some non-universal behavior at the beginning, and then we will quickly approach the universal plateau that is the prediction of Poisson. Okay, but so the question is, we have all this phenomenology, but can we prove something? Is there a way to actually establish with a certain degree of rigor, or even with some intuitive argument why this holds. This is highly non-trivial. So up to a few years ago, what was available was a proof of the quantum chaos conjecture based on the semi-classical periodic orbit theory. It was a very interesting and extremely detailed heuristic proof, if you want, so counting the number of semi-classical orbits and matching and writing the spectral form factor using the so-called Gertz-Wheeler formula. Then there was also a rigorous proof of the quantum chaos conjecture for a certain class of few particle systems, the so-called fully connected incommensurate quantum graphs. But the question remained of what about many-body systems that are far from any semi-classical limit, where I can't apply any of these arguments. So, for example, systems of fermions or spin halves. And also, what about the Barry-Tabor conjecture? So all these proofs here are not assessing this. So what I'm going to discuss today is that there has been some interesting recent progress in studying this particular topic, precisely using duality and quantum circuits. In particular, here I'm listing a small selection of works. There are certainly some that I'm missing. And in this talk, in particular, I will try to describe the first set. So I will try to describe the results of these mainly these three papers that I have worked on in collaboration with Pavel Kos, that used to be in Ljubljana and now moved to Munich, and then Tomas, who we all know. Okay, so I think it's a good point to ask questions on this general setting, because then I will move on to the quantum circuits formulation. So if you have any question at this point, I will be happy.
Can I ask something?
Yeah, sure.
Maybe this is not very relevant, but what happens to those curves that you saw when there is a weak integrability breaking?
So yeah, that's a good question. So you're saying what happens when, like, which one of these two I will see if there is a weak integrability break?
Yeah, weak integrability break.
Well, it's a very good question. I think the answer will be I will see some mixture of the two. It won't be a very clear-cut case, I don't think. So I mean, if there is a weak integrability breaking, then ultimately the system is non-integrable. So right. You would expect to see something like that, no?
Right, absolutely.
But it won't be so simple. It won't be so simple. If you do it in practice, then you will see that it's some sort of mixture of the two. But maybe if you look at large enough times, you will, so exactly. Short enough energy scales, you will indeed be able to see.
So there should be a crossover. There should be some sort of a crossover time.
Yeah, I think so.
Which is set by this integrability breaking parameter.
Yeah, actually, so it's not exactly this, but later in the talk, I will show an example where you indeed see these kind of crossover times in certain quantum circuits. But yeah, I think this is a good expectation.
Cool.
I think so.
Cool.
Thanks. Sorry, can I a naive question maybe?
Sure.
Hi, ciao. So
go ahead.
So these plots are at finite size, I'm assuming. These curves yes. For the spectral form factor. So is there a way in which, if you look at the infinitesimal size, these scales to something meaningful?
That's also
or
a very good
this
question.
Intrinsically?
No, this is also a very good question. So in the example I will consider, indeed, I will be able to take the thermodynamic limit. So that will scale to something meaningful. But the question is, what does this time here do with the system size, right? So because imagine that this time here scales with the system size, grows with system size, then when we take the thermodynamic limit, we see none of the universal behavior. And typically for many-body systems, at least for those with some conservation laws, this is exactly what you expect. So when there is a conservation law in the system, which can also be the energy, for example, if it's a closed system, then you expect this T here to scale like the size of the system squared. And the argument is very simple. It's based on the fact that there is diffusion in the system. So every time tau t will scale with the system size, you will not be able to study this problem meaningfully in the thermodynamics.
Because I'm asking, because, for example, this quantity in integrable systems you could probably compute, but also always in the scaling in the thermodynamic limit where you take the infinite system size first, like this trace of u to the t, like if you take some integral spin chains. But then this is not what you probably what you want.
I think this is an extremely interesting question. One has to probably look at the quantity and see if there is some sort of non-trivial limit that one can take. But yeah, naively, I would say that if this time here scales, then we are in trouble. But for integrable models, I really don't know what to expect for the analog of this time. So for this thing here, I don't really know what to expect. So yeah, but it's something definitely worth looking at.
So Bruno, I had one more question.
Yes.
So in general, if your generic quantum many-body system would have a classical limit, won't it be in some sort of a mixed phase space? Like between regular and fully chaotic. It would be in some sort of a mixed phase space. So then what do I expect for the level statistics? And
so I'm not sure I understand the question. But the short answer to that is that I don't know. So I know what to expect for the case where the classical limit is chaotic, but I mean, when it's mixed, maybe we can discuss later. I don't know.
I'm actually looking at a paper which says generic Hamiltonian dynamical systems are neither integrable nor ergodic. Maybe I can put it in the chat box and maybe we can discuss it later.
Yeah, we can. I mean, it's a very interesting point. I just can't add much on that, unfortunately. I don't.
Please go ahead.
Okay. So we were saying, okay. Are there any other questions on that? No? Okay. If not, let me then proceed with the main part of the talk. So let me try and study this quantity, this spectral form factor, in quantum circuits. So, okay, so this would be a very difficult slide to unpack, but fortunately, Peter did a great job in explaining all this diagrammatic notation already. So this would be a lot easier for me now. So, okay, so if you write the spectral form factor here, we are trying to compute the expectation value of the absolute value squared of the trace of u to the t. Okay, so the absolute value squared of the trace of u to the t can be thought as the trace of u to the t times the trace of u dagger to the t. So the trace of u to the t we can represent with this red part of the circuit here. So we take again our nice brickwork quantum circuit where these are the two-side gates. We also put some non-trivial one-side gates. Why not? And so this one here is just trace of u to the t. Okay. So in blue instead, I'm picturing trace of u dagger to the t. So basically, all gates here, all blue gates here, are the Hermitian conjugate of the red ones on the upper part of the circuit. Okay. So now I want to consider, and also let me also stress that here I'm for the moment taking generic quantum circuits on qubits. So each one of these wires here has generic d internal states. So let me now consider the situation where I take the two-side gates, so these red and blue boxes, to be fixed. So they are just some u and w. Sorry, I'm calling u and w. So you see here there is some sort of staggered structure. So I can, to be more general, take this gate here, this paler red gate here, to be different from the dark red gate here. Okay, so and I call the two one u and the other one w, and then they are repeated throughout the circuit. They are the same in all the circuit. Instead, I take these one-side gates. So these,
yeah. Is the blue color one, is it DAG? What?
So this blue here, this blue two-side gate is the DAG of this red one.
Yeah.
Okay.
Okay.
While Well, these, unfortunately, this is really not an amazing choice of color, but this other blue here is just some one-side gate, okay? So this is a one-side gate, and this gray one is the Hermitian conjugate of that. Okay, so instead, so I take the two-side gates, so these bigger boxes, to be fixed, while instead, I want to take the one-side gates to be random. But how random? So I take them random and independently distributed in space. So for example, these and these and these and these are just random matrices independently distributed. But I take them repeated in time so that I have a well-defined time evolution operator. So basically, this matrix here is the same as this matrix here, is the same as this matrix here, and so on. Okay. And the average, which is an integral part of the definition of the spectral form factor, I take over these random one-side matrices. Okay. Okay. Any questions on the setting, because this is a bit convoluted? Okay. So I hope the setting is clear.
Yeah, Bruno.
Yes.
So
please.
Yeah, I understand the setting, but this average. In a
yes.
typical setting, you would average or a very, I mean, see, the average is needed because this quantity is not a self-averaging one.
Exactly.
So,
exactly.
But this at the same time seems to me a bit extreme in the sense that you're averaging for, yeah.
That's a very good point. So first, in a normal setting, you would average either in time, you can even do some sort of windowing in time, or you can average over some external parameter of your system. I don't know, you can put a magnetic field and you average over the magnetic field or something like that. So this kind of averaging is exactly like that. Because here I didn't say what is the distribution. I can take a distribution that is extremely narrow,
okay,
right? Which is a very, very weak.
Okay.
I'm not saying these are not hard random, for example. The distribution is not specified.
All right, thanks.
The only requirement on the distribution is that is factorized in space. So different points in space are independently distributed. This is crucial, but that's the only requirement I'm making.
Okay, thanks.
Okay.
Yeah.
Other questions?
Thanks. No, that's good. Thanks.
Thank you. Okay, so let me move on. Okay, so now to simplify the manipulations, let me just do what other people before me already did today. So let me fold. So what I will do is I will take the blue part of the circuit and bend it underneath the red part. So I will obtain something that is the green gate here. So the green portion here, which is defined by these green gates that are, as you see, just the superposition of red and blue. And these two are the Hermitian conjugate of one another. Okay, good. So let's look now at the spectral factor. We can write it like this then. And now we use the property that I already stressed, which is that the average that I'm taking is factorized in space. Okay, and for this reason, instead of writing it like that, I can equally well write it like this. Okay, so you see here I'm bringing the average inside, and since the average is factorized, these two quantities here are equal. But this means that if I consider a single one of these columns, of this average of this set of gates, and I call it T, this is nothing but a transfer matrix in space. So I can rewrite my spectral form factor as the trace of some transfer matrix T, which is this quantity here, to some power L. Note that here I took the distribution at each point to be the same. So, but in principle, you can also do something different. You can take the distribution at each point to be different. There will be some changes, which maybe I will have time to discuss. Okay. But so with this simple manipulation, what we did is we wrote the spectral form factor in terms of this matrix, or since it's we are considering traces of its powers of the spectrum of a transfer matrix T. Note that T is not dependent on space, so it doesn't depend on L at all. Okay, so the only dependence on L in this equation is really just here in this power. So since since T is L independent, the large volume behavior of this quantity of the spectral form factor depends only on the largest eigenvalues of the transfer matrix. And let me just make this final general remark for this treatment. I can repeat the same if I want to look at higher moments of the spectral form factor. So if instead of the trace of u to the t squared, I want to look at the trace of u to the 2n, like this one, I can again repeat exactly the same manipulations and write it as the trace of some transfer matrix that now will depend on n to power L. And this transfer matrix will be written exactly as the T now, but with the only difference that the green gates will be made piling up n red gates and n blue gates instead of only two. Okay, very good. So basically now we rewrote our initial problem. We wanted to compute the spectral form factor, and we wrote the spectral form factor in terms of traces of powers of some transfer matrix. So the question is, can we characterize the spectrum of this transfer matrix? Well, remarkably, yes, we can do it in some special cases. So let me discuss a few of them. But before that, maybe was that clear? Do you have any question on this? Good. So let me move on to discuss some of these special cases. So the first case I want to consider is we take U and W, so the two-side gates, to be dual unitary gates of the following form. Okay. So where here Uj, so the small u, U1, U2, U3, U4, are single-side unitary matrices, completely general. While S here is the swap gate, which we already encountered this morning, is just the gate that permutes, that flips the states in two neighboring qubits. And S3 instead is the third component of the spin, or of the, it's the third component of the spin, so this parametrization here is not the most general parametrization for dual unitary circuits if one looks at local Hilbert spaces D that are larger than 2. So this is all dual unitary circuits in D equal 2, but whenever one looks at D larger than 2, then this is just some sort of partial parametrization. Okay. But if I look at gates of this form, then I can basically rewrite the problem of finding the spectrum of T as a simple algebraic problem. So what I mean is the following. One can prove the following theorem. So the maximal eigenvalue of T in this case, for these gates, is 1, irrespective of the distribution of the disorder. And the corresponding eigenvectors are in one-to-one correspondence with the solution of the following algebraic problem. So basically, I know that the maximal eigenvalue of T is 1, but I need to understand how many ones do I have in the spectrum. And to find the number of ones, I need to find the number of solutions to this problem, which is finding all matrices that commute with these two objects, MA and MAB. Okay, let's gradually unpack that. So MA here is nothing but a generalized magnetization on the time lattice, but where we take only odd or even sides on the time lattice. So here this sigma is a generalized Pauli matrix. Okay, so this is like a generalized SUN magnetization, but where I'm only looking at even or odd lattice sides, at a sublattice made of even or odd lattice sides. while MAB is a very similar quantity, but now instead of looking at just the magnetization, I'm looking at the product of two generalized Pauli matrices on two neighboring sides. And AB here are spanning over from 1 to the squared. So they are the numbers of the generators of SUD. Okay. So this is already a remarkable statement. So one can prove that all the maximal eigenvalues of T are in one-to-one correspondence with the solutions of the following algebraic problem. The second statement is that actually this problem can be solved exactly. So this algebraic problem for these particular gates can be solved exactly, and one can prove that the only solutions to the previous problems are the only linearly independent solutions of the previous problem are matrices of this form, where pi 2t is just a periodic shift to one side, for example, to the right, in a chain of t sides, or 2t sides, sorry. So basically, the only matrices that commute with both MA and MAB are the translations. So it's clear immediately that these kind of translations commute with these two magnetizations. This is obvious because they generate shifts that are of an even number of sides, and these are manifestly written in a translational invariant way. But in principle, you can have much more, many more operators commuting with these two. What you can prove is that instead, this doesn't happen. So that immediately allows us to find an interesting result concerning the spectral form factor. In particular, we find that the spectral form factor in the thermodynamic limit is equal to T, okay? So this is exactly equal to the thermodynamic limit of the result for the CUE random matrices, okay? So in this case, we showed, so there was this, the question of Lorenzo before. So in this case, we showed that this tauless time, so the time after which the the concrete system will follow random matrix, is actually doesn't scale with L. It's actually 0 in this case, okay? And for this reason, one can think of these systems as some sort of critically chaotic systems. So where in the thermodynamic limit, the spectral form factor is exactly equal to the thermodynamic limit of the spectral form factor of random matrix theory. So, okay, but once again, so here we just showed that there is this agreement for a single probe of spectral correlations, because as I said, the spectral form factor is only probing 2-point spectral correlations. So what can we say for the others? Well, one can do basically the same thing also concerning higher moments. So once again, we can prove the analogous theorem. So also, when looking at the maximal eigenvalues of Tn, which is the transfer matrix determining the higher moments, one can prove that the maximal eigenvalue of Tn is 1, and the corresponding eigenvectors are in one-to-one correspondence with the solution of the following algebraic problem.
Hi, Bruno.
So, yeah, sorry.
Yeah. So you have, loosely speaking, 5 more minutes, and then we'll have maybe 5 more minutes of question and answer. So a gentle alert.
Thanks a lot. Sorry. Yeah. Okay. Okay. So okay. So let me go quickly on that. It's the same idea. The point is that in the generic N case, we can't solve exactly this problem. So what we find is that we find a number of solutions that are okay. Doesn't matter the exact form. So we find a number of solutions, and we can prove then that our spectral form factor is at least larger or equal than the result for CUE random matrices. But actually, numerical experiments are suggesting that this bound here is saturated, so that also the higher moments in these systems obey random matrix theory. So one can repeat the same treatment considering a particular subclass of dual unitary circuits where we impose by force time reversal symmetry. So these can be done by fixing some of these matrices to be the transpose of the other. And so if one, for example, chooses these gates here and also imposes a constraint on the disorder, then this ensures that the propagator is time reversal invariant. And in this case, we can repeat again our analysis, and we can again formulate the equivalent theorem. In this case, to find all the eigenvectors one of the transfer matrix, one has to find all the solutions to this algebraic problem, where the difference from before is that the matrix, the operator MAB is replaced by the sum of itself and its reflection symmetric counterpart. And in this case, once again, we can't solve this problem explicitly, exactly, but we find a number of solutions. And once again, we can write a bound for the spectral form factor, and we find that the spectral form factor is larger or equal than 2t, which is the result expected for COE random matrices. Okay, in the third example that I wanted to consider in the talk is a different example. So I don't want to look at dual unitary gates anymore. Let me consider some different gates that are not dual unitary. So let me fix v equal to and take two-side gates that are diagonal, are just like this. And then I fine-tune the disorder distribution in such a way that the disorder is present only once every two sides. So the spectral from the diagrammatic representation of the spectral form factor is something like that. And you see here there is no small ball, you see. So here there is no disorder in this along this column, along this column, and along this column there is no disorder. So for these systems, one can prove explicitly that there is a complete set of local integrals of motion, and they have finite support. In particular, they have support 3. So these systems are localized and provably localized. We name them strongly localized circuits because these local integrals of motion have a finite support 3, whatever J is. Okay, so for these systems, one can again use the machinery of before and prove that the transfer matrix Tn, so the one that describes all the moments of the spectral form factor, has only a small non-zero block. It's all zero apart from a small block of size 4 to the n times 4 to the n. So time independent. It doesn't depend on time. It only depends on the moment that we are looking at. For example, if you look at the spectral form factor itself, the matrix is 4 by 4. And moreover, it has a unique maximal eigenvalue. So we can write the spectral form factor in a form like that, at least for large volume. So, okay, but now we found some systems that are localized. So, okay, the first question that we want to study is, okay, do we find something similar to integrable systems in this case? We have a complete set of conserved charges, so do they behave like integrable systems? So does it become Poissonian for large enough times? And the quick answer to that is no. So it has the same spectral form factor as the Poisson result, but all the higher moments are not Poissonian. Okay, it only agrees with Poisson for n equal 1. For n larger than 1 is qualitatively similar, this result here, to a matrix of this form, to the spectral form factor of a matrix of this form. Basically, a matrix composed by a number of disconnected Poisson patches. So here you see I'm taking a small Poisson matrix of support psi, and then I'm taking the tensor product of all of them. So this is really disconnected in space. So the spectral statistics of a matrix like that, it's not Poissonian. It is not Poissonian because the Poissonian spectral statistics, it's not conserved under tensor product multiplication. And so basically what we see here is that our system behaves like these disconnected patches, but the size of the patches changes with time. So at very large times, the size becomes something of the order of 3, but it is smaller before. And it has this nice 3-step profile. And so the last point I want to mention in the talk is this generic. So this kind of behavior in the higher moments of the spectral form factor, this interesting 3-step profile in the higher moments of the spectral form factor, is that something generic? So to answer this question, we considered a generic Floquet MBL system, and we plotted the same quantity. So you see, so this is the result for strongly localized systems, and this is for the Floquet MBL. And basically, the result is that, yes, the same kind of qualitative behavior is observed. The main difference is that if one looks at short enough energy scales, the generic MBL system, at least at fixed volume, approaches the Poisson result, okay? But only in the short scale. While instead, at intermediate scales, it again behaves as this disconnected Poisson.
Hi, Bruno. So how much time you need?
I'm done.
Oh, okay.
I'm finished. Yeah. So,
okay.
Yeah, sorry. So with that, I can briefly wrap up. So I just wanted to show you examples where space-time duality can lead to exact results for the spectral statistics of quantum circuits. And I showed you 3 examples. Okay, so thank you very much for your attention, and I'm happy to take any questions if you have them.
Thank you so much, Bruno. Very interesting. So we might have time for one quick question.
Okay.
Can I ask a question? Sohail here.
Sure.
Yeah, please go
ahead. My question is on the strongly localizing circuits. So first,
sure.
The building block of this is, can you just go to that slide? Yeah.
Yeah.
So these gates will be, these gates will be like in the dual unitary case, they will be maximally entangled, and they will be UR.
They will be.
These will be unitary with respect to partial transpose, right?
Exactly. Exactly. So it's basically in the language of Carol's talk, this would be the other line, right? Not the dual unitary line, the other one that was intersecting.
Right.
Yeah. So exactly, precisely.
One, and second thing is I'm aware of one work on this so to speak localizer models by John Chalker's group, where they have on-site disorder, like you have these one-site disorders, and there are diagonal interactions, and essentially your U and W are also diagonal. And
yes,
showed for what was interesting in their result was like for qubits, for all interaction strengths, it was always in MBL phase, but for Q greater than 3, they had both MBL and ergodic phase. So do you expect some sort of behavior for Q equal to 3 or for Q traits a bit different behavior, or in the sense that you don't have localization?
Well, this is an interesting question. I think it is hard to tell, because the point is that in this case, I mean, for the results on dual unitary circuits, the local space dimension doesn't really play a role. But here, it's actually quite important, because the result is based basically on the fact that you are taking the product of these two transfer matrices, the one made of this darker green and lighter green, and there should be nothing in between. So it's a very fine-tuned thing. So I don't know if this is preserved when you increase the local space dimension. I should look at it. The quick answer is that I don't know.
Second,
because, I mean, let me just stress an important fact. So this is a lot stronger than MBL, because this kind of localization holds for any J. For any J, you can choose whatever coupling you want, and you will still be localized. This is not what happens if you put disorder everywhere, which was the example I was showing at the end. Then you see this localization behavior, at least at fixed L, for J that is small enough. So you have to take J small. But for these systems, this is not necessary. So it's really a very strong localization, the one enforced here. So yeah.
Yeah, associated question. So, do you expect this behavior in higher dimension also, where the partial transpose is unitary kind of thing, is the other line?
I think that was.
I think it's very hard to answer. Okay. Let's say no, but I don't have good intuition, let's say, for that.
Thank you.
Thanks.
Actually, I'm aware about your recent work on these strongly localizer circuits and all. So I was also curious about your the value of J. You had shown some plots that you had taken J. So I was just thinking, because I mean, I'm thinking in terms of entangling these gates as entangling gates. So for example,
so you mean in this plot here, for example?
Yeah. So your
here,
J,
I think.
Yeah, what's the value of J you are taking here?
I think it's 10 to the minus 4, if I remember correctly. So it's really very small.
Oh, it is really small. Okay.
Really, really small. And you see, also, I didn't have time to discuss that in detail, but it's interesting how these transitions here are scaling with J. In particular, the first one scales like 1 over J, and the second one scales like 1 over J squared. So it has, I mean, to me, it reminds me of some sort of Fermi golden rule kind of argument for the second transition, where, I mean, but yeah, again, it's another thing that I still.
Okay, thank you very much. Thanks.
Thanks.
Okay, with that, we thank Bruno again, and I'll introduce the next speaker, Eliseo.